Hello students, welcome back. In this video we are going to be going through Chapter 7, Section 3, Estimating a Population Standard Deviation or Variance. The last two videos we did population mean and population proportion, and we're going to continue with the concept that if we have a sample and then we measure the sample standard deviation, can we make a inference about the population based on that sample? So the key concept here is we are going to present a method for using a sample standard deviation or sample variance. Remember, variance is just the standard deviation squared to estimate the value of the corresponding population standard deviation. Notice the symbols. Sample standard deviation is S. Population standard deviation is lowercase sigma. Again, we have the point estimate, which is saying that the sample variance is the best estimate, like the best guess as to what the population will be for both variance and standard deviation. And we are going to construct a confidence interval. So when constructing a confidence interval, estimate of a population standard deviation, we will construct the confidence interval using a chi-square distribution. Okay, what is that? Well, the chi-square distribution, which is chi is the pretty much like the x symbol right there. X squared, chi squared, or chi square. So in a normally distributed population with the variance sigma squared, if we randomly select independent samples of size n, and for each sample compute the sample variance, the sample statistic is chi squared equals n minus 1 times the sample deviation squared divided by the population standard deviation squared. And that is called the chi-square distribution. So again, you have your population, you're doing a sample of that with the size n, and just like we did for population proportion or population mean, we have a formula for how to do that distribution. But now we have a chi distribution. Okay, what does it look like? Well, previously in population proportion and population mean for the Z and T tables, we had a normal distribution where we had the bell-shaped curve, the mean was right in the middle. Now the chi-square distribution is non-symmetric. It is skewed to the right, meaning that a lot of the values fall on the left-hand side. Skewed to the right, think of your right toe, where your big toe, your area under your toes is most of the values fall on the left-hand side, so skewed right. Other things to note is that the values along the x-axis over here, it starts at 0, and then it just goes up from there. So the values could be 0 or positive, but cannot be negative, which is different than the normal distribution where the standard is you have 0 in the middle, anything to the left is negative, anything to the right is positive. So again, for the chi-square distribution, all the values are 0 or positive. So the critical values, we denote right tail critical values by chi r, and we call left tail critical values chi L squared. So those critical values can be found using the technology or table A4. So to recap, we use table A2 for section 7.1, we use table A3 for section 7.2, and now we are going to use table A4 for section 7.3. Again, similar to previously, or I guess the last section, that to use that table we have to determine the degrees of freedom. The degrees of freedom, very similar to the last section, is going to be the sample size minus 1. So n minus 1 gives you your degrees of freedom. And the chi-square distribution is different for each number of degrees of freedom. As the number of degrees of freedom increases, the chi-square distribution approaches a normal. So degrees of freedom is 10, very skewed. Degree of freedom is 20, less skewed, but still skewed. And as that degrees of freedom increases, we get more and more normal. So here's an important slide. because the chi-squared distribution is not symmetric, a confidence interval does not fit the regular format where you have your actual population is going to be bounded by the sample minus the margin of error to the left, and then your upper bound being the sample plus the margin of error. It's not going to be that anymore. We have to do separate calculations for the upper and lower confidence value. So if we are using table A4 for finding critical values, note the following design features of the table. In table A4, each critical value of chi in the body of the table corresponds to an area given in the top row of the table. And each area in that top row is a cumulative area to the right. This is an important part, to the right of the critical value. When we do an example, I think that will solidify what the text is saying. But what you have to note is that it's not symmetric. So you have the area to the left right here, and then the area to the right here for, say, a 95% confidence. Those two, it's not going to be the same value along the chi x-axis. So let's find an example. Now we are just finding the critical value. So a simple random sample of 22 IQ scores is obtained. Construct a confidence interval for the population, standard deviation, S, required to the left and right critical values of chi corresponding to a confidence level of 95% and a sample size of n equals 22. Find two critical values because we have to find chi L and chi R. So now we have to find chi L squared, the critical value of chi squared separating an area of 0.025 in the left tail, and chi R squared, the critical value of chi squared separating an area of 0.025 in the right tail. Okay. So again, these values are very different. So we need to do it twice. So with a sample size of n equals 22, the number of degrees of freedom would be 1, or that value minus 1. So degrees of freedom is 21. Using table A4 and a cumulative area of 0.975, notice how we did that. So like we said, the table gives you the cumulative area to the right. So if we know that we want there to be 0.025 area to the left of it. So in order to use a table, if you do 1 minus 0.025, you get 0.975. So we use this table to get chi L to have a cumulative area to the right of 0.975. With the degree of freedom of 21, we get that chi L squared value to be 10.283. Now for chi R, we want to get the cumulative area to the right, so now we're looking at where the area is going to be 0.025. Note the difference right there. This is where most people are making their errors. Again, degrees of freedom is 21, gives us a chi value of 35.479. Let me say that one more time, because I can just foresee there being errors with this. The chi distribution gives you the cumulative area to the right of the critical value. We know our critical value is right here, and we want to get the cumulative area, well, the chi value is given based on the cumulative area to the right. So since we know the cumulative area to the left of that is going to be 0.025, 1 minus 0.025 will give us 0.975. So we know that this chi value is going to be corresponding to a point right here, and that value is going to be 10.283. For chi R, it's going to be 0.025 to the right. So we don't have to do 1 minus anything. It's just going to be 0.025 directly. With degrees of freedom of 21, we get the chi is going to be 35.479, as shown on table A4. Okay. So, like mentioned on the previous slide, chi R squared is going to be 35.479, which is the critical value to the right. And that's more straightforward since we locate 21 in the degrees of freedom column at the left and 0.025 across the top row. Chi L, again, is 10.283, but we must locate 0.975 or 1 minus 0.025 across the top row because the values in the top row are always areas to the right. Okay, so now once we get the chi values, now we can create our confidence interval. So confidence interval for estimating a population standard deviation or variance. So here's your notation again, nothing new except for chi. We have our population standard deviation, which is lowercase sigma. Lowercase sigma squared is population variance. Lowercase s is sample standard deviation. S squared is sample variance. N is number of sample values. E is margin of error. And then the chi values we just talked about. So the requirements. Again, the sample must be a simple random sample. And 2, the population must have normally distributed values. The requirements of a normal distribution is much stricter here than in earlier sections, so large departures from normal distributions can result in large errors. It's very sensitive to it. So it must be a normal distribution. The confidence interval. So it's a little different. It's, again, because it's not asymmetric, you can't just say it's the sample variance or sample standard deviation plus the margin of error minus margin of error like we did previously. Here's how we calculate the actual confidence interval for population variance. And then here is your standard deviation. Again, note that the standard deviation is just the square root of the variance. So we have n minus 1 times the sample standard deviation squared, or sample variance, divided by chi r squared, which is less than the actual population variance, which is bounded to the right by n minus 1 variance squared divided by chi l squared. So we're saying that the actual population variance is bounded by here to the left and here to the right. For population standard deviation, very similar formula, but we are taking the square root of all 3 segments to now have it be in terms of standard deviation and not variance. So just a round off rule, when using the original set of data values, round the confidence interval to 1 more decimal place than is used for the data. So if you have the standard deviations of a random set of data, whether it be weights of elephants, and you measure it to the nearest whole pound, we want now the standard deviation and variance to be rounded off to the tens place. So you always use 1 more decimal place than what your original data was measured off to. So if we, instead of giving a list of data values, we know that the sample size and the sample standard deviation, now we can round the confidence interval to the same number of decimal places. So procedure for constructing a confidence interval for sigma or sigma squared, sample standard deviation, or a population standard deviation, or population variance. 1. Verify the 2 requirements are satisfied. 2. Use n-1 degrees of freedom. Find the critical values chi r and chi l that correspond to the desired confidence level. That's using table A4. 3. To get a confidence interval estimate of the variance, use the following. This formula right here. The actual population variance is bounded to the left by this and to the right of that. We are whatever % confidence that that statement is true. And then to get a confidence interval estimate of sigma, take the square root of each of these sides. So same formula, just square root of each side. And then round the confidence interval limit using the round off rule. So if your n and s was calculated off of a list of data, it's going to be 1 more decimal place than what your data was measured using. And if you were given s and n, then you can just use the same amount of decimal places as was shown. All right, let's look at an example. So we have data set 7, IQ and lead in Appendix B. Again, your book will give you plenty of examples of data values and measurements and random surveys. So this is IQ and LID in Appendix B. It lists IQ scores. So the 22 full IQ scores for the group with the median exposure to lead group 2 have a standard deviation of 14.29263. Construct the sample to be a simple random sample and construct a 95% confidence interval of sigma, the standard deviation of the population for which the sample was obtained. Okay, so we have our sample. We know how many people, we know the sample standard deviation, and we want to create a 95% confidence interval for the population. So how to solve it? Step 1, check the requirements. The sample is treated as a simple random sample. 2, the accompanying histogram has a shape close to a normal distribution, so yes, we will say that the requirement check is satisfied. Step 2, use table A4. Okay, so we have n equals 22, so the degrees of freedom is 21. Refer to the row corresponding to 21 degrees of freedom, and then refer to the top columns with areas of 0.975 and 0.025. So then we get the critical values of 10.283 and 35.479, which happen to be the same ones from the earlier example, I believe. Next, we can use these critical values and the sample standard deviation and the sample size of n equals 22 into the formula to determine the confidence interval. So we have our formula here, plug in your values, plug and chug, and then you're off. So once you have this value, then if you want to, we don't want the variance. This is the confidence interval for the variance. We don't want that. We want the confidence interval for the standard deviation. So we then take the square root of 120.9 and the square root of 417.2. And this will give us the 95% confidence interval estimate of the population standard deviation. And now we can apply rounding over here, and here would be your final answer. So interpretation, based on this result, we have 95% confidence that the limits of 11 and 20.4 contain the true value of S. The confidence interval can be expressed as 11.0, 24.4, but it cannot be expressed in this format because of the way the distribution is shaped. Another type of problem is determining the sample size needed. So the procedures for finding the sample size necessary to estimate sigma are much more complex than for means and proportions, and that's because of the way it's shaped. So for normally distributed populations, the table on the following slide, or I guess it's right below, can be used. So in this case, the complicated formula is made very simple for you. All you have to do is just read the chart. So to be 95% confident that that S is within 1%, 5%, 10, 20, 30, 40, 50, then you can use an n sample size of at least these many numbers. So obviously, the more confident you are, the more sample size you need. And the less confident you are, the smaller sample size you should need. So then this table right here is for 95% confident, 99% confident. So StatDisk also provides samples as well. See the Word document that is included within the module. So finally, let's just do a quick example. We want to estimate the standard deviation sigma of all IQ scores of people with exposure to lead. We want to be 99% confident that our estimate is within 5% of the true value of sigma. How large of a sample should it be? Assume the population is normally distributed. 99% confident that our estimate is within 5% of the true value. Let's go to this table. 99% confident that our true value is within 5%. 1,338. Let's see if we are correct. Okay, so from the table, we can see that 99% confident with an error of 5% corresponds to a sample size of 1,338. So we should obtain a simple random sample of 1,338 IQ scores from the population of subjects exposed to lead. All right. Any questions, let me know. I do think that this section was a little more complicated than section 7.1 and 7.2. So any questions, please feel free to reach out to me.